we have gone through the definition of finite automata. We have discussed the various terms like transition table. We have discussed about the extended transition function, right? And we have discussed about what is a deterministic finite automata. Also, we have prepared some diagrams related to different regular languages. Now, to prepare a very complex diagrams, what we can do that we'll see in the session. So our goal is, you can see the screen now. So our goal is, I will see that if there are regular languages which are complex, how we can divide that complex problem into a small problem, and then we can find the answer of that complete problem. So if you look at this slide, you will find that the first regular language is a very simple language. So can you recognize the first regular language in this diagram? It is indicating, if you look at the pattern which is accepted by the first regular language or finite automata, so you can see it accepts. If anyone can write in the chat window. So what is the first language? It accepts any strings having odd number of zeros. You can see if first zero is there, it is accepted. If there are 3 zeros, it is accepted. If there are 5 zeros, it is accepted. It is accepting all the strings in which there are odd number of zeros present. So can anyone tell what is the second language? L2. What is the L2 language? So in L2 language, if you look at this picture, yes, you can write your answers in the chat window. So will it accept this? Yes, you can see it is ending with Q2. It is ending with Q2. Right? You can see it is ending with Q2. So you can see in this diagram that 0, 0 and after 0, 0, if anything is there, so it will accept it. Okay. So if we write something like this, so basically we can say if there is a substring 0, 0, if there is a substring 0, 0, it is accepted by the given language. If there is a substring 0, 0, it is accepted by the given language. Okay. If there is a substring 0, 0, it will accept that particular pattern. Otherwise, it will not accept the pattern. So now what we want to do, we want to find the intersection of the two languages. That means it must have odd number of zeros. So if you consider L1 intersection L2, then it is must have odd number of zeros and contains substring 0, 0. Both criteria must be satisfied. Right? If you consider L1 intersection L2, then both have odd number of zeros in it and it contains substring 0, 0. Then it will be accepted by this intersection. So to generate the intersection, what we have to do, we have to find the new states for that automata. So it will be 2 into 3, that is equal to 6 states. We get total 6 states, 2 states from the first one and 3 states from the second one. So you can see here that capital Q1 is the set of states of the first automata and capital Q2 is the set of states of the second automata. So when you consider the set Q, it is an ordered pair. You can see. So the first state is P0 Q0, then it is P0 Q1, then P0 Q2. Similarly, we have P1 Q0, P1 Q1, and P1 Q2. So this is how we'll get 6 different states. The input alphabet must be same for both. For the intersection operation, the accepting state. Now the rule is that if it is an intersection, both criteria must be satisfied. So if the ordered pair contains accepting states of both the automata, if the ordered pair contains accepting states of both the automata, then and then it is a part of the final answer. So our final state or accepting state will be only one here, P1 Q2. It will be only P1 Q2 because you can see in P0 Q1, P0 Q0 there is no accepting state. P0 Q1 there is no accepting state. In P0 Q2 only one accepting state is present. We require both the states in intersection operation. Similarly, in P1 Q0 only one accepting state is present, so it is not valid. P1 Q1 and last P1 Q2. Only P1 Q2 is the state in which we are having both the accepting states. So we'll consider that. Definitely the start state will be P0 Q0. So when we define these parameters, set of states, input alphabet, accepting state, start state, we must define the transition function, which is very important part of automata. So to describe the transition function, what we are doing, we are considering any state like P0 Q2, as you can see here. As you can see here, P0 Q2 as example. On input symbol 0, on input symbol 0, we are finding the output states. So now you can see that we have the ordered pair as a state. In this transition function, we have ordered pair as a state. So we'll apply the transition function delta 1 of the first automata on the P0 state. We will apply the transition function delta 2 of a second automata on the Q2 state on input symbol 0. So you can see P0 on input 0, it is going to P1. Q2 on input 0, it is Q2. So the output state is P1 Q2. That is P1 Q2. Similarly, we can find out all the transition functions. So here let's see that how we get the final output. So to understand the thing, here both the original automatas are given. Now we start with the initial state. As you know, we start with the initial state P0 Q0, and from P0 and Q0 on input 0, we are going to P1 Q1 state. From P0 Q0 on input 1, on input 0, we are going to P1 Q1 state. From P0 Q0 on input 1. So it is self loop. So you can see the self loop in the P0 Q0 state. Okay, are you getting this? Now we are generating the new automata. You can see in this new automata there are 6 steps. All the combinations 2 into 3. Yes, any query up to this? Yes, are you getting this diagram? Okay, now from P0 Q0, new state which is reachable is up P1 Q1, right? We are getting the new state which is reachable is the P1 Q1. Here we have to be careful that only the state which is reachable from the original state, only the state which is reachable from the original state we have to consider. So P1 Q1 is reachable from P0 Q0. Now we solve the P1 Q1 for input 0 and 1. So from P1 on input 0, it is P0. Q1 on input 0, it is Q2. So we are getting a new state P0 Q2, and this P0 Q2 is reachable from initial state. Now from P1 Q1 on input 1, we are getting P1 Q0 state. You can see P1 on input symbol 1 will get the P1 state. From Q1 state on input 1, we will go to Q0 state. So we are getting P1 Q0 as a new reachable state from the original state. Right? We don't have to randomly select the state. Only the states which are reachable from the original one, we have to select one by one. So now we can consider P0 Q2 state. So now from P0 on input 1, it is P0. Q2 on input 1, it is Q2. P0 on input 0, it is P1. Q2 on input 0, it is Q2. So we are getting one more reachable state from the initial state, that is P1 Q2. It is P1 Q2. Now from P1 Q0 state, from P1 Q0 state, we'll check 0 and 1. So P1 on input 0 will go to P0 state. From Q0 on input 0 will go to Q1 state. P1 and Q0, there is a self loop of 1. So now the only state which is left we need to check is P1 Q2. So now P1 Q2 on input 1, it is P1 Q2 itself, and P1 Q2 on input 0, it is P0 Q2. From P1 Q2 on input 0, it is P0 Q2. So now this is how we get the complete diagram. Now up to this step, the procedure will be common, right? Up to this step, the procedure will be common. Now to show the intersection, the only rule is both the states must be accepting states. To show the intersection of the automata, we have to consider only the accepting state as the state in which both are accepting states. So that's why P1 Q2 will be the accepting state of this final diagram. So now we can see that a string which is only valid in the first one, like we can say odd number of zeros, right? Odd number of zeros, 0, 1, 0, 1, 0. You can see it is valid in the first automata, 0, 1, 0. You can see 0, 1, 0, 1, 0. It is valid in first, but it is not valid in the intersection. Okay, can you tell in which state this pattern will end? In the intersection automata. Can you tell which state this pattern will end in the intersection automata? Yes, can you identify the state? Because as per the automata 1, it is valid, but it is not valid as per the automata 2, because it does not contain the substring 0, 0. So when this pattern will end, what will be the final state? Just you can look at the diagram and you can trace this pattern, 0, 1, 0, 1, 0. It is valid in the first automata. It is valid in the first automata. So if you start from the first, symbol is a 0. From the initial state, which is the initial state? P0 Q0. Right? As per the first automata, we must have odd number of zeros only. So if you traverse from the initial state on input 0, you will go to P1 Q1 state. right? You will go to P1 Q1 when you traverse 0. When you traverse 1, you will go to P1 Q0. From P1 Q0, again you will traverse 0. You will go to P0 Q1. From P0 Q1, when you traverse 1, you will go to P0 Q0. And from P0 Q0, when you traverse using symbol 0, you will go to P1 Q1 state. So final state is P1 Q1. It's P1 Q1. So now you can see that P1 Q1 having a P1 as an accepting state because the string is valid as per the automata 1. But Q1 is not an accepting state because string is not valid in the automata 2. Similarly, we can consider another example. Okay, where 0 0 will end up? The 0 0 is valid in L2. It contains the substring 0 0. Contains the substring 0 0. So 0 0 is valid in L2 language. So where this 0 0 end up? In the intersection diagram, it is a P0 Q2. Why it is P0 Q2? Because it is valid as per the second language. So Q2 must be there. So it is Q2. And it is not valid as per the first language. So it is P0. Now if we take this example, zero 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 string, where it will end up? Is it valid in both the diagrams or no? Yes, it is valid in both the diagrams because it is having odd number of zeros and also it has substring 0 0 present in it. So where it will end up in the intersection diagram? What will be the final state if you traverse this string 0 0 0? Yes, it will be P1 Q2. Why? Because P1 it is valid and Q2 because it is also valid in automata 2. So this is how you can do the intersection of this two regular languages and you can solve the complex problems. You can see what is the problem, that we want to find a automata for the language which is having odd number of zeros and substring 0 0 both. So now what we have done, instead of drawing a diagram directly, we have constructed the L1 diagram first, which is very simple, odd number of zeros. We have constructed a diagram for L2 language having a substring 0 0 and then we are applying an intersection operation. So you can create an automata with 6 states very easily with this method. So I hope the point is clear. Right? So we have to go step by step. So normally you will find this kind of diagrams in 8 marks in the exam for any complex language. So this is how we can define this thing in the form of theory. This is what we have discussed so far. Right? We have two automatas, M1. So for M1 we are using the state P0, P1, P2 in this theorem, and we are writing Q1 as the set of states of first automata, sigma which is common, delta 1 transition function of the first automata, P0 initial state, and F1 the set of accepting states of the first automata. Now for the M2 machine, we have a Q2 set of states of the second language, sigma, delta 2 the transition function for the second automata, Q0 initial state of the second automata, and F2 that is the set of states of the second automata. So L of M1 is equal to L1. This indicates that all the strings which are valid in the L1 language are accepted by machine 1 and it is not accepting any extra string. So both are equal. Similarly, L of M2 is equal to L2 indicates that all the strings which are valid in the L2 language are only accepted by the machine 2. No other strings are accepted by the machine 2. And to construct the final diagram, we are applying this Q sigma F and the transition function. So in a general form, if we write this transition function, we can write like this. for any pi state of the first automata and any qj state of the second automata, we have to consider the all input symbols of the sigma. So we are considering 0 and 1 both. So we are using a variable a here to represent it, right? On the pi state, we have to apply input symbol a using the delta 1 function, and on the qj state, which is of second automata, we have to apply a delta 2 function, and we'll get again the output state, which is an ordered pair, So now let us consider one more interesting example. Regular languages are closed under intersection. So as you can see, the first regular language is a plus ba. So is it a deterministic FA? Is it? Is it deterministic FA? The first and second? Or they are not deterministic? We have discussed this term deterministic FA in the previous session. Is the first diagram a deterministic FA? Yes or no? Reason is that from the Q0 state, there are two outgoing arrows for input symbol A and B. From Q1 state, the outgoing arrow for B is missing. Similarly, from the Q2 state, outgoing arrows for A and B both are missing. So you cannot determine the complete steps. So it is not deterministic FA. Similarly, in the second diagram, it is accepting the language which is a finite language A, BA and BBA. Only these three strings are accepted, A, BA and BBA. But it is also not deterministic FA, because for the P2, input symbol B is missing, and for P3 also you can see that A and B are missing. So now when you perform the intersection, ideally how many states do we have? It is 4 into 3, that is equal to 12. That is equal to 12. We need 12 states to construct the intersection diagram. Right? 3 states from the L1 language and 4 states from the L2. So 3 into 4, we require total 12 states. Now as you can see, in the final diagram, which pattern should be accepted? It should accept A and BA because it is the intersection. It is the intersection. So if you only consider the reachable states from the origin state, you can see that in the P0, Q0 on input A, they are going to Q2, P3. They are going to Q2, P3. So it is reachable from the original state. Similarly, from P0, Q0 on input B, they are going to P1, Q1. From P0, Q0 on input B, we are going to 1 Q1 state. Okay, now from Q to P3 and we are missing. Now from P1, Q1 on input A. From P1, Q1 on input A, we are going to Q2, P3. We are going to Q2, P3. Yeah. Now similarly from Q1, P1 state, B is missing. From Q1, P1, B is missing. But because it is intersection, we are not worried about it. Because it is intersection, we are not worried about it. Because you can see that intersection will only give the elements which are present in both the languages. They are present in both the languages. So this will be a very simple diagram with 3 states. So you don't have to go for all the outgoing arrows, right? It is not required. You can see we are only considering 3 arrows. From P1 on input B, we are not considering. From P2 on input A, we are not considering. Is it clear? You can see P1 on input B, we are going to P2. We are not considering that state. Similarly, P2 on input A, we are going to P3. We are not considering that because they are not reachable from the original state. They are not reachable from the original state. So we don't have to consider that in the intersection. So this is what I am talking about, the intersection process. Why it is intersection? So that it has common elements of both the languages. It has common elements of both the languages. Okay, now let us see one more diagram. So you can see here. Okay, can you identify the first language and the second language in this diagram? Again, we have two languages, L1 and L2. So what is the first language? Let us take this example too. What is the first language? Which strings are accepted in the first language? You can see that A is an accepting state, B is also an accepting state. Yes. A should not be a substring. If A is present, we will go to a dead state. So it does not contain the substring AA. Right? That is the correct answer. A is not the substring which is accepted by this finite automata. Okay, what is the second language? What is the second language? You have to focus on the two circles, right? Concentric circles, two concentric circles, because they are the accepting states of this automata. Yes, what is the second language? So as per you, if we add this, is AB a varied? It is accepted by the second finite automata. Is AB accepted by the second automata? No, it is not accepted. So what is the language? The second automata is indicating ending with AB. Yes, it is ending with AB. So now here you can see 3 into 3. Total we have 9 states in effect for intersection. That is what you can see in the diagram also. There are 9 states. A with P, A with Q, A with R. B with P, B with Q, B with R. C with P, Q and R. So you can see these 9 states. Now the initial state is AP. Okay, which are the accepting states? Can you identify for the intersection? Which are the accepting states? For intersection purpose? Which are the accepting states? In this diagram it is not shown. It is not shown in this diagram. Which are the accepting states? What is the rule? That for the intersection purpose, we have to only consider those states in which accepting states of both the machines are present. We have to consider only those states in which accepting states of both the machines are present. Yes, can anyone write AR and BR? Yes, AR and BR. That is the correct answer. We have two accepting states, AR and BR. But now if you observe this diagram, you will find that BR is not reachable from the starting state. When you start with AP is our starting state. So from AP, you can go to BQ on input A. From BQ on input A, you will go to CQ. From BQ on input B, you will go to AR. From AR on input A, you will go to BQ. From AR on input B, you will go to AP. From CQ, you can reach to CP. You can reach to CR. From CR, you can reach to CP also. But you cannot reach to AQ state, PB state, and BR state. That is what you cannot do. So that's why only accepting state of the intersection is the AR state. Only accepting state of the intersection will be the AR state. Right? We will not consider the BR. Now one more thing you can observe, that here the between BQ and CQ there is input A, and once you go from BQ state to CQ, you cannot return from the CQ state, right, to BQ or any another state. So the BQ on input A is acting as a bridge. BQ on input A is acting as a bridge for the diagram. And this CP, CQ and CR, once you enter into that state, you will remain in that state. So we can replace this CP, CQ and CR as one dead state. We can replace CQ, CP and CR as one dead state. Because once you reach to CQ, you can either go to CP or CR, but you cannot return from that. So, and this CP, CQ and CR are not accepting states. The most important thing is CP, CQ and CR are also not accepting states. So we'll replace CQ, CP and CR as one dead state. I hope it is clear now. So now if we consider the diagram for intersection, we are getting this diagram. As you can see, it is shown here. It is shown here in the diagram D. It is for the intersection purpose. It is for the intersection purpose, diagram D. So you can see any string which does not contain AA, right, and ends with AB is accepted. So you can see BAB is accepted. BAB is accepted. It is ending with AB and does not contain AA. Only AB is also accepted, right? A, B is also accepted. Only B is accepted. Here can you find there is one small problem with this diagram. Can you see that there are two outgoing arrows from initial state, right? There are two outgoing arrows from this initial state on input B, right? There are two outgoing arrows from the initial state on input B. So which one is correct out of these two? Right? Which one is correct? Self loop is the correct arrow. Right? Self loop is the correct arrow, as you can see in the previous slide. Right? There is no arrow from initial state to B. There is no arrow from initial state to B. Right? You can see that the direction of arrow is not correct. You can see direction is from AR to AP. The direction is from AR to AP. Is it clear? The direction should be from AR to AP. So the direction of arrow is not correct in this diagram. I hope you can understand this thing, because there cannot be two outgoing arrows. So direction should be from this AR to AP. So direction is incorrect. Right? It should be in the reverse direction. Is it clear? Okay, now let us focus on the union part. So only difference between the intersection and union is that in case of a union, right? If any one of the state is an accepting state, because the definition will be either it should not contain the substring either it should not contain the substring or it should end with AB. Either it should not contain the substring or it should end with AB. Any one criteria should be satisfied. So you can see AAB is a valid string in the union. AAB is valid in union. Because it is ending with AB. So in case of union, if one of the state is an accepting state, so as you know, A and B are accepting states of L1 and R is an accepting state of L2. R is an accepting state of L2. So you can see that AP, because A is an accepting state, so AP is shown with a double circle. BQ, B is an accepting state of the L1, so it is shown with a double circle in union. AR, right? So it is also a valid because both are accepting states. Now also you can see CQ, CR, so CR having a C and R, it is an accepting state because R is an accepting state. So you can see that AAB pattern is accepted in CR, right? AAB, it is a valid pattern ending with AB and it is accepted in CR state. So you can see the only difference is if you go for union operation, the number of accepting states will be more, because if any one of the state is an accepting state, then it will be the accepting state of the union operation. If both the states are accepting states, then it will be an intersection operation. If both the states are accepting states, then it will be the intersection operation. So in case of union, if any one of the state is an accepting state, then it is a union operation. Is this clear? Difference between union and intersection? Is it clear? Okay, so now let us proceed further. Let us take this example for the union operation. We have two languages, A and A, and here in the second diagram you have A plus BA and BBA, and we'll apply the union operation. So the question is the above union correct? Is the union operation correct? Which strings are accepted by these union operations? Which strings are accepted by this union operation? Which strings are valid in the union operation? Either a string should contain A, or it should contain BA, or it should contain BBA. Union means valid strings of both. It is a union of valid strings of both. Your L1 language is having only two elements, A and BA. Only two elements are in L1 language. L2 language, three elements, A, BA and BBA. When you perform a L1 union L2, it should be A, BA and BBA. because it is a union of two languages. It is a union of two languages. It is a superset. It is always a superset. So here you can see that when you perform a union operation, right, you cannot directly generate the states like this. Right? You cannot generate the states like this. What you have to do first, you have to add the date state. You have to add the date state into the diagrams. Right? For intersection, it will work. Why it is working for intersection? The reason is because intersection takes common elements of both the languages. Intersection takes common element of both the languages, while a union operation includes all the valid strings of both the languages. So first we have to modify the diagram. We have to add the date state. I added the date state as QD. QD in the first automata. I have added the date state in second automata, that is PD. Right? P0, P1, P2, P3, and PD. It is the date state. Right? Also, you can have a link from accepting state, that is Q2 to PD on A and B. Similarly, we have a link from P3 to PD. Right? So once you add this date state, right? Once you add the date state, because you can see there are no outgoing arrows from the accepting state. Right? So here, because there are no outgoing arrows from the accepting state, we are not showing arrows to date state. And now if we draw the diagram, you can see the diagram of union. Now we have 4 into 5. 20 states are in the diagram. 4 into 5, that is equal to 20 states. That is equal to 20 states. So now when you consider the final diagram, you can see that the string A is accepted, then string BA is also accepted, and the string BBA is also accepted. Right? You can see this thing, that string A is accepted, string BA is accepted, and string BBA is also accepted. And it is the valid operation. It is the valid operation. And you can see which are the accepting states. If any one of the state is an accepting state, it is the accepting state for the union operation. So Q2, P3, Q2 and P3 is an accepting state. Similarly, QD-P3, you can see QD-P3, because P3 is an accepting state and QD is a non-accepting state, but it is the accepting state for the union operation. It is the accepting state for the union operation. While QD-P2 is not accepting state, Q1, P1, no accepting states present in it, and Q0, P0, no accepting state is present in it. Okay, so now when we consider the third important operation, that is known as the complement operation. Let us consider the complement operation, right, on the regular languages. So now when we consider the complement operation on the regular languages, it is very straightforward. Just we have to revert the states. Accepting state becomes a non-accepting states. Non-accepting states you can see in this first diagram that it does not contain the substring AA in the first language in L1, right? It does not AA substring. When you take L1 dash, it is the complement, or we can say L1 bar, it contains substring AA. Right? So you can see the complement. You will convert A into a non-accepting state, you will convert B into a non-accepting state, and you will convert C into accepting state. So it contains substring AA. If there is a substring present, it is accepted by the complement. It is accepted by the complement operation. Similarly, if I consider the second diagram, a string ending with AB. So what will the complement? Any string which is not ending with AB, right? L2 dash, if we define, so we can say any string not ending with AB is accepted. Any string which is not ending with AB is accepted by this diagram, by the complement of L2 language. So in that case, P and Q will be the accepting states and R will become the non-accepting state. Yes, any query in this complement operation? Is it clear? Yes. Any query in this? Okay, so now the small thing which is left, that using the concept of this union and intersection, we can prove a certain thing like this. That suppose we want to prove that languages are closed under intersection. We want to prove that languages are closed under intersection. So what we'll do, we'll assume two things. Do this thing, we'll assume that they are closed under complement and union. That means what? If you find a complement of a regular language, it is a regular language. Because we can get the automata for it. Similarly, if you perform a union of two a regular language, the output will be also a regular language because we are getting the automata for that language. So this is what we are assuming, that they are closed under complement and union. So complement of a regular language is also regular, and union of a regular language is also a regular language. So now we'll assume that L1 and L2 are regular languages. So complement of L1 and complement of L2 are also regular languages as per our assumption. Also we know that union of two regular languages is also regular. So we'll take complement of L1 union with complement of L2, and it is a regular language because we are assuming the other two parameters. Now again we'll take the complement of this union. We'll take the complement of this union. So we'll say that complement of union of L1 complement with union of with L2 complement is also a regular language. So L1 dash. So we'll get L1 dash dash. We'll get L1 intersection L2. Right? That is a De Morgan's law. We know that A dash A intersection B whole dash is equal to A dash union B dash. And similarly, reverse scenario we have. Right? That is what we are using here. That L1 intersection L2 is a regular language. That is what we can prove using the two assumptions. And similarly, we can prove for the union. So now to prove for the union, we'll make another two assumptions. That RLs are closed under complement and intersection. It will assume this thing, that regular languages are closed under complement and intersection. Using this two assumption, we can prove that regular languages are closed under a union operation also. So again, we'll take in the same way that L1 and L2 are regular languages. Definitely L1 complement and L2 complement are regular languages. Now we'll use another assumption, intersection. So L1 complement intersection with L2 complement. L1 complement intersection with L2 complement is a regular language. Again, we'll use the first assumption, that is complement of a regular language is a regular language. So complement of L1 complement intersection with L2 complement is a regular language. So this will give us, as per the De Morgan's law, that L1 union L2 is a regular language. That L1 in union L2 is also a regular language. So is this clear? Any query in this? Right? So using these two assumptions, we can prove the third thing. We have to make an assumption of any two things, and based on the two things, we can prove the third thing. So any query in this? Yes? Do you have any query in this? So today I'm getting a less response. I'm getting a response from only 3-4 students. Rikin, then Harsh. Right? I can see only 2-3 names today. I hope it is clear. It is not very difficult. Harpreet has given the answer, then Bhumit has given the answer. Sahil has given the answer. Abhi has given the answer in the beginning. Shail has given. So, yes. Is this clear? Okay, so now, as you know, that definitely I will upload the slides in the Google Classroom, so you can refer to it of this week. Okay, now the main thing which you want to know: syllables of. So you have to use, as you know, this book. It is the 3rd edition, and from chapter 1, syllables will be 1.1 and 1.5. From chapter 3, which I have covered, we have 3.1, then we have 3.2, 3.3, and 3.5. So now if you go through this book of TOEFL, right, you may have a doubt that what you should prepare. So definitely different examples you have to prepare. Along with that, there are some theory portions. So you can see that these are the theory portions in the book. Basically, it is in the form of gray color. Right? These theory portions are in the form of gray color in the book. You can see a block of gray color, which is indicating the theory portion. If you have a book right now, you can also check along with this as I am checking. And we have taken the new examples so that you have more clarity. Right? We have not covered the examples which are exactly given in the book. We have taken new examples in these slides. We have more examples. We can also take the examples from straightway from the book as it is, but we have taken some additional examples as well. Right? We have taken some additional examples as well. Right? So these are the gray blocks of your chapter 3, which are the theorems and definitions. Yes, if you have any query right now, you can ask regarding the syllables of my portion. This I am talking about chapter 1 and chapter 3 only. Right? And as you know that it will be a descriptive mode. for the TOEFL, right? It will be the descriptive mode for this subject. Yes, if you have any query regarding the chapter 3 or chapter 1, any query, you can write down in the chat window, because later on if you raise any query, it will be difficult to answer, and as well as it is difficult to communicate to all. I can communicate to only one student, or maybe the one who has raised the query. So if you have any query, right, you can ask me and I will answer that question. And definitely I am sharing this material today so that you can also refer these 2 lectures easily. Yes. So you may have a doubt, right, that 3.4, so that 3.4 will be covered in the second sessional, because the topic is related to second sessional. So that's why it is not right now in the first internal. Right? We'll cover the 3.4 completely from the book, but it is related to second sessional. Some of the topics we'll reuse in the second sessional from 3.4. So that's why we are combining with the second sessional. Yes, any query from your side? And it will be a descriptive mode. So I hope there are no queries anymore from your side. Everything is straightforward and clear. So let me take your attendance quickly. Let me go through this number of people present in this, and then we'll end this session. It is 2, 8, 22, 27, 28, 46, 47, 49, 51, 53, 57, 58, 59, 60, 62, 68, 85, 88, 90, 107, 108, 116, 118, 119, 124, 126, 127, 135, 139, 145, 146, 153, 161, 164, 167, 169, and 179. So this is all about the attendance. So thank you all. I am ending this session now.